Hello, it's Professor Gavor again. We're looking at the same data set, this table 4-6 from the econometrics book by Gujarati and Porter. And we're trying to predict GDP of a variety. We have this actual data from a variety of countries, and we're trying to see, would be the dependent variable is GDP. And we're also trying to see if we can use education and population to predict GDP. In the first video, we looked at a simple linear regression using the graphical techniques available in Excel. This time, I want to go to data, and I want to look at data analysis, and I want to do regression. If you don't have data analysis, and Google installing data analysis Excel, Mac, or Windows, depending on what you have, and they'll give you instructions for installing it. It's pretty easy, and it's a full statistical package. Real working serious statisticians don't think highly of Excel's statistical capabilities. I'm not sure that I would recommend that, therefore, that you use them for real life and death applications, but for training purposes and classroom purposes, it's more than adequate, I believe. So I click on regression, and it says, where's my input range? Well, I want to add the GDP column. That's my dependent variable. That's my Y variable. And notice that I even included the title. Now, if I go to input range, and let's say I want to just do population the first time, and I go through and I highlight that, I've got that, and now I click on labels because I do have the labels in the top of the columns. And I want to have an output range as opposed to a new spreadsheet, or I could do a new spreadsheet, but I think I'll use an output range, and I'll put this output right there. Do we want residuals or residual plots? We could look at a residual plot. Why not? And a normal probability plot, which will be stuff we'll use later. We won't use that in this first level of analysis. So if I go there, now all of a sudden it has my analysis of variance table. And you can see here that my R square is 20.9, which it was over here. And adjusted R squared is 0.1871. You can look up what that means in a book. We're not going to cover that right now. And in the analysis of variance table, we have this significance. The F-test for the regression is very, very low. So if the null hypothesis is that there is not a valid regression. Now look at it. It's the same as the T statistic, p-value, and this T statistic, that statistic is different, but the significance is the same here and here. Because this T statistic here, the null hypothesis is that the population, the coefficient of the population, this coefficient is 0. That's the null hypothesis says there's no regression model here. There's no regression model here with the F-test. But when you get down into this bottom part of the analysis variance table, it does it by the coefficient of variable by variable. Well, there's only one variable, population. That's why the p-value is exactly the same. The alternative hypothesis is that the coefficient of population, the slope in this case, is not 0. So given that we have a p-value of 0.003, it's lower than 0.001, so at a very small significance level of alpha equals 0.001, we would say that we would reject the null hypothesis and accept the alternative hypothesis that the slope or the coefficient of the population variable is non-zero, and Therefore, we can assume that this is a valid regression model. So that adds to the visual display. And if we go over here and look at, we can look at normal probability plots, and we can look at residual plots. We'll cover that in a later chapter, maybe even with the same data set. The residual is basically the actual minus the predicted. That would be the residual value. So what do we have here? We want to look at R squared and adjusted R squared. You want to look at that. You want to look at this significance level for the regression. And you want to look at these for all the variables. You want to look at the t-statistic and a p-value, and for your hypothesis testing. This tells you also, it gives you a upper 95 and lower 95% confidence intervals on the value of the slope. So here is where we see the coefficients. We'll highlight that maybe in a different color. Let's make it orange. So that if we go over here, we'll see that 2461 is a slope, and 4394.6, 4395 is in fact the y-intercept. So there's lots of things. Here's your sum of squares, and notice that it's in scientific notation, so it's 9.57 times 10 to the 10th power times 10 to the 11th power times 10 to the 11th. You take the ratios of those, and from that ratio you calculate your F statistic. Here's your degrees of freedom, one for regression, one for residual, one for total, and that influences what the F statistic will be and what the significance value will be. Tells you the number of observations. So the analysis of variance gives you a lot of output. So let's try it now for our other one. So if I go to data, I go to data analysis, and I go to regression again. Well, it keeps everything that was in there before. In this case, so I'm going to do it in a new worksheet so you see how that does. My y values are the same, but I'm going to change my x values. I want my x values to be this way. I want it to use population, and it wants to use education to predict GDP. And remember from our previous example, and I can leave everything else the same and just say OK. And you see that it added a worksheet. And if I'll have to toggle between the two, but it's added, it looks the same, but my R squared is 94.3%. So that's really awesome. Now, if you look at the significance level, it's way more impressive. It's 7.63, but times 10 to the minus 23rd power, which means that it's, if I'm doing this, it's a valid regression. There's no regression model. There is a valid regression model being the alternative hypothesis. I'm going to reject the null hypothesis, and it's valid, and it's very, very significant. 7.63 times 10 to the minus 23rd, that means decimal place 22 zeros, 0.763. And if I was to make this as a number, it's going to come out as 0. No matter how many, I have to go 22 decimal places. On the 23rd decimal place, I'll see another number. So it's essentially 0. It's very small. And you'll see that I have the same down here for the t statistic as well, the same level of significance. So this is an important model. Here is the regression coefficients. And if we go back to the original model, we will see that 0.943 was R squared, 19.432, 95.145, and what do we get here? So this is a ANOVA table, and what do we call this? GDP versus education. Oops, I can't spell, but other than that, I'm doing very well. So what have we done so far? We've looked at a simple linear regression using a simple graphical technique, and now we're looking at, we looked at the same two outputs, but we looked at using an analysis of variance table and looking at the associated hypothesis test and where the significant things you would pick off of this analysis of variance table. So what we talked about before is when we talk about confidence intervals and tolerance intervals. Tolerance intervals are wider than confidence intervals, but for this estimate of 2461, the upper 95% confidence interval could be 407.8, and it could go as low as 8.43, which means while this is our best regression estimate, that you see if I really want to put a confidence interval around it at 95%, it's a pretty wide range. It could, if I collect data again a couple years later, it could change. I think if you look at all the countries in the world and their education, it's basically your population, so you've probably got a decent model here. I would, again, if we're just doing one, I would go with GDP versus education. Thank you very much, and look forward to the next video.